Hi students, in this session we will discuss about the time domain specifications of a control system. We have discussed about the second order system and we have gone through the various responses corresponding to underdamped, critically damped, overdamped and undamped cases in the case of second order system, and we have concluded that in the case of second order system, critically damped case will give the correct response. Okay, when we are giving the step input, the output of the critically damped second order control system will have a similar curve at the output corresponding to the step input. So the desired performance characteristics of control systems are specified in terms of time domain specifications, and the desired performance characteristics of a system of any order may be specified in terms of the transient response to a unit step input signals. And the transient response of a practical control system often exhibits damped oscillations before reaching steady state. A typical damped oscillatory response of the system is shown in the figure, and you have gone through this type of response when we discussed a underdamped case in the case of second order system, and when we give an input of step, when we give a step input, the output response of the second order underdamped case is like this, and you can see that in this curve there is a rising portion and also there is an oscillatory nature. So this represents the damped oscillatory response and it is corresponding to the second order system, and here various sessions of this output curve is marked, like in the time axis TD is marked, TR is marked, TP is marked, and these are corresponding to delay time, rise time, peak time. TD is corresponding to delay time, TR is corresponding to rise time, and TP is corresponding to peak time, and MP is maximum overshoot, and also there is another time, that is TS, that is settling time, and it is corresponding to allowable error 2% or 5%. So now we are going to the transient response of a practical control system, and in that we can see that it has a oscillatory nature in the response, and the transient response characteristics of a control system to unit step input is specified in terms of the following time domain specifications, and the 5 time domain specifications in the case of transient response are delay time, rise time, peak time, maximum overshoot and settling time, and all these times are marked in this curve, and this is corresponding to a damped oscillation response of a second order system, and the 5 time domain specification in this case are delay time TD, rise time TR, peak time TP, and maximum overshoot MP, and settling time TS. Okay. Next we will go to the statement of every time specification, that is first is delay time. The delay time is the delay time is TD, and it is the time taken for the response to reach from 0% to 50%. So you can see that when we go upwards from the TD, it will meet the curve at a point where output response is 0.5. That means TD corresponding to the time taken for the curve to reach 50% of its maximum value. Okay, so that is TD. So its definition is delay time. It is the time taken for the response to reach 50% of the final value for the very first time. And next is the rise time. So it is the time taken for the response to rise from 0 to 100% for the very first time. You can see here rise time is TR, and it is time taken for the curve to reach from 0% to 100%. So see at TR, the curve meets TR when the amplitude value is 1 or response is 1. That means it is the time taken for the curve to reach 0% to 100% for the 100% value for the very first time, and but for overdamped system it is the time taken by the response to rise from 10% to 90%. You can see that in the case of overdamped, you might remember the output or response curve for the overdamped system. You can see that in that case the output does not have a oscillatory nature, but its amplitude will be lesser. So we can say that its rise time in the case of overdamped system is the time taken by the response to rise from 10% to 90%. So, and also for critically damped system, it is the time taken for the response to rise from 5% to 95%. And next is the peak time. Peak time is the time taken for the response to reach the peak value for the very first time, and it is the time taken for the response to reach the peak overshoot. You can see that TP is marked corresponding to TP, the amplitude is very high, that is it is corresponding to the maximum value. Okay, so TP is the time taken for the response to reach the maximum value or maximum overshoot. And next is the peak overshoot MP, and it is defined as a ratio of maximum peak value to the final value. That means peak overshoot is a ratio, and it is the ratio of maximum peak value to the final value, and where the maximum peak value is measured from the final value. So let's see, infinity is the final value of C of t, and C of Tp is the maximum value of C of t. So peak overshoot MP can be represented as C of Tp minus C of infinity divided by C of infinity. That means you know that the original value of the we are giving the step as the input. That means its value is 1. Step input has a value 1, but the output corresponding to step input is not have the same value as 1. You can see that here the output goes to a maximum value and it is beyond the value 1. Okay, so the final value of the output is not exactly the value corresponding to C of Tp, right? That means C of Tp is the maximum value that the curve attains, but C of infinity is the final value. We are assuming that the system will get the original value at infinity time. That means it will goes to the steady state at a time which is equal to infinity. So we can say that C infinity is the final value of C of t, and C of Tp is the maximum value of C of t. So peak overshoot MP can be written as C of Tp minus C of infinity divided by C of infinity. And percentage of peak overshoot can be found out by C of Tp minus C of infinity divided by C of infinity into 100. You should remember this relationship and it will be useful for doing problems. And next is the settling time TSA. It is defined as the time taken by the response to reach and stay within a specified error, and it is usually expressed as percentage of final value, and the usual tolerable error is 2% or 5% of the final value. You can see that settling time is marked here, and it corresponds to a value corresponding to allowable error 2% or 5%. That means at the settling time the response will settle to a particular value. That means its oscillatory nature is reduced at the settling time value, and the allowable error is 2% to 5%. That means we cannot completely eliminate the error. So there will not be a exact value at TS. There will be some error at TS. And the next is the expression for, we have these are the time domain specifications, that is delay time, rise time, peak time, maximum overshoot and settling time are the time domain specifications, and these values are used to characterize the control system when we are giving a unit step input to that control system. Okay, so and these characteristics will say about the system response. Okay. Next, we will go to the expression for this time domain specifications. First, we will derive the expression for rise time, that is TR. For that, we are taking the underdamped response of the second order system, and that you have studied in the previous sessions. First of all, you should remember the response of an underdamped second order system for unit step input, and I am writing it has here the unit step response of second order system for underdamped case is given by C of t equal to 1 minus e raised to minus epsilon omega n t by square root 1 minus epsilon square into sin omega dt plus theta. This is the equation for underdamped case in the case of second order system, and the curve that we have familiarized, that is this curve is corresponding to that equation. That means that equation contains a sine terms and exponential terms. So this curve also contains an exponential rise portion, and also the sinusoidal portion is also there in this curve. You can see that this part represents the exponential part, and this is oscillatory in nature, that is sinusoidal term. So this is the curve corresponding to that equation. So C of t is equal to 1 minus e raised to minus delta omega n into t divided by square root 1 minus epsilon square into sin omega dt plus theta is the unit step response of the second order system for underdamped case. And here we want to find out the rise time Tp. So at rise time t equal to Tr, that means that time will be Tr, and so the response C of t will be C of Tr, and we know that at rise time that will be equal to 1. That means C of Tr equal to 1 minus e raised to, you know that how I got the value 1. We know that at rise time at Tr the response will reach the value 1. That is its definition. That means the curve will rise from 0% to 100% at rise time. We know that unit step is given as input, so its maximum value is 1. So the output will have the maximum value of 1 at rise time. Okay. So we will take the value of C of Tr equal to 1, and C of Tr is equal to, we have the equation 1 minus e raised to minus delta into omega n into Tr divided by square root 1 minus delta square into sin omega dtr plus theta, that is equal to 1. And we can rearrange this equation by taking 1 on same side. So we will get e raised to minus epsilon omega n into Tr divided by square root 1 minus epsilon square into sin omega dtr plus theta equal to 0. And since minus e raised to minus epsilon omega n into Tr not equal to 0, the term sin omega dt into Tr plus theta equal to 0. Here you can see that this product term will be equal to, you can see that the product term will be equal to 0. That means that either this term will be equal to 0 or this term will be equal to 0. You can see that when this is equal to 0, that means this is a e raised to minus term. That means once this is equal to 0, then this will corresponding to infinity term. So this will not be 0. Okay. So sin omega Tr plus theta will be equal to 0. That means we can represent it as sin phi equal to 0. So phi will be equal to 0, pi, 2 pi, 3 pi, etc. And omega dtr plus theta equal to pi. So that value of angle will be equal to pi. So omega d into Tr equal to pi minus theta. See, also here we can note one thing, that if you are drawing a triangle with theta as the angle between delta and square root of 1 minus epsilon and square root of 1 minus epsilon square, then tan theta will be equal to square root of 1 minus epsilon square divided by epsilon. You should remember that also. And when tan theta will be this value, then theta will be equal to tan inverse of square root of 1 minus epsilon square minus epsilon. And we have an expression omega d Tr equal to pi minus theta. So rise time Tr will be equal to, by rearranging that equation, we will get pi minus theta divided by omega t. We know that theta equal to tan inverse square root of 1 minus epsilon square minus epsilon. So damped frequency oscillation we have we have familiarized with the equation omega d equal to omega n into square root 1 minus epsilon square. So rise time TR will be equal to pi minus c. Instead of theta we are substituting tan inverse of square root 1 minus epsilon square divided by epsilon, and instead of omega d we are substituting omega n into 1 square root 1 minus epsilon square. And so that is the equation for rise time, and here theta equal to tan inverse square root 1 minus epsilon square divided by epsilon should be measured in radians. So you should remember the equation for rise time. Equation for rise time TR will be equal to pi minus tan inverse square root 1 minus epsilon square divided by epsilon whole divided by omega n into square root 1 minus epsilon square. Also rise time has another equation, TR will be equal to pi minus theta divided by omega d. These two equations you should remember and should be helpful for doing problem. So we have got the equation for rise time, and next we want to find out the peak time. You know that peak time is the value corresponding to the maximum value of the response. That means at the peak time the response will take a maximum value. So to find the expression for peak time, that is Tp, we know that the differentiate is c of t with respect to t, and the function will be maximum when its first derivative will be equal to 0. So we have the condition for peak value as d by dt of c of t at t equal to Tp will be equal to 0, and we know that the equation for c of t, that is we are considering the underdamped case of the second order system, and we are giving unit step as input, and its response we know that c of t equal to 1 minus e raised to minus delta omega n into t divided by square root 1 minus delta square into sin omega dt plus theta. So you should by heart this equation in order for deriving peak time, settling time, maximum overshoot, etc. So you should by heart this equation, okay. And in order to find out the first derivative with respect to time, that is d by dt of c of t, we can find out the derivative. It is a product of two terms, so you should use the rule of first function into derivative of second plus second function into derivative of first, so that you will get this equation like this: e raised to minus delta epsilon n into t into minus epsilon omega n plus sin omega dt plus theta plus minus e raised to minus delta omega n into t divided by square root 1 minus epsilon square into sin omega dt plus theta has a first derivative has a cos omega dt plus theta into omega d. So we know that here omega d equal to omega n into square root 1 minus epsilon square. We can substitute that value and we can rearrange the equation as d by dt of c of t equal to e raised to minus epsilon omega n into t divided by square root 1 minus epsilon square is common, so it can be taken outside, and the rest of the terms are delta sin omega dt plus theta minus square root 1 minus epsilon square into cos omega dt plus theta. And we can see that here we can substitute delta as cos theta and square root 1 minus delta square as sin theta, because we know that we have a trigonometric relation sin theta sin square theta plus cos square theta is equal to 1. If cos theta is equal to delta, then square root of 1 minus delta square will be sin theta. So we can write the equation as omega n divided by square root 1 minus delta square into e raised to minus delta omega n into t into cos theta into sin omega dt plus theta minus sin theta into cos omega dt plus theta. And this is the form of sin a cos b minus cos a sin b. So that will be equal to sin a minus b. So we can write in the same formula, that is omega n divided by square root 1 minus epsilon square and e raised to minus delta omega n into dt into sin omega dt plus theta minus theta. So that will be equal to sin omega dt, and the complete result is omega n divided by square root 1 minus delta square and e raised to minus delta omega n into dt into sin omega dt. That is the first derivative. But in order to get the peak value, that is Tp, and the first derivative will be equated to 0. So d by dt of c of t will be equal to 0. So omega n divided by square root 1 minus delta square and e raised to minus epsilon omega n into Tp into sin omega dt into Tp will be equal to 0. Here e raised to minus delta omega n into Tp will not be equal to 0. So sin omega dt into Tp will be equal to 0. And we know that sin theta is equal to 0 for the values of 0, pi, 2 pi, 3 pi, etc. We are taking the first value of theta as pi. So omega d into Tp will be equal to pi. So peak time Tp can be found out by Tp equal to pi by omega d. That is an important equation. That is peak time has an equation pi divided by omega d. And the damped frequency of oscillation omega d is equal to omega n into square root 1 minus delta square. That this equation also you should by heart. And peak time can be obtained by substituting the value of omega d, such as Tp equal to pi divided by omega n into square root 1 minus delta square is the epsilon square is the peak time. See, when I am explaining this, I am using instead of epsilon as a delta. That is my mistake. You should remember that symbol is epsilon. Okay. In some cases it is in some textbook it is given that this symbol is a delta, but you should use epsilon epsilon term for indicating that. Okay. So the expression for peak time is Tp is equal to pi divided by omega d, and another expression for Tp is equal to pi divided by omega n into square root of 1 minus epsilon square. These two equations you should by heart. Okay. And next is the peak overshoot. And you know that peak overshoot is measured as the difference between the maximum value to the peak value. Okay. It is the ratio of maximum value to peak value. So peak overshoot in percentage can be found out by the equation Mp equal to C of Tp minus C of infinity divided by C of infinity into 100%, where C of Tp is the peak response at T equal to Tp, and C of infinity is the final steady state value. And the unit step response of the second order system is given by C of t equal to 1 minus e raised to minus epsilon omega n into t divided by square root 1 minus epsilon square into sin omega dt plus theta. And we have to find out the value of C of infinity by substituting t equal to infinity. When C of t equal to C of infinity, then we can substitute the value of infinity instead of t, so that we will get 1 minus e raised to minus infinity by square root 1 minus epsilon square. That will be equal to 1 minus 0, that is equal to 0. That means e raised to minus infinity will be equal to 0. So that will give you the value of C of infinity as 1. Next we can substitute for C of t equal to Tp, that is equal to C of Tp will be equal to, we can substitute for T as Tp. So we will get C of Tp equal to 1 minus e raised to minus epsilon into omega n into Tp divided by square root 1 minus epsilon square into sin omega d into Tp plus theta. And here 1 minus we can have the value of C of Tp as 1 minus e raised to minus epsilon into omega n into Tp will be equal to pi by omega d, that divided by square root 1 minus epsilon square into sin omega d into pi by omega d plus theta. And again we can write it as omega, here you can write omega d will be equal to omega n into square root 1 minus epsilon square. So that will be equal to 1 minus e raised to minus epsilon into omega n into pi by omega n into square root 1 minus epsilon square into sin omega, here omega d and omega d get cancelled, so we will get a sin pi plus theta divided by square root 1 minus epsilon square. And here also one omega n and omega n term will be there, so it will be cancelled, so that we will get 1 plus e raised to minus epsilon into pi divided by square root 1 minus epsilon square whole divided by square root 1 minus epsilon square into sin pi plus theta will be equal to minus sin theta. And so there are two minus signs, so it will change to plus. So we have the equation 1 plus e raised to minus epsilon into pi divided by square root 1 minus epsilon square divided by square root 1 minus epsilon square into square root sin theta equal to square root 1 minus epsilon square. See, you can have the triangle like this, and in this case you can see that sin theta will be equal to, if epsilon is one side and square root 1 minus epsilon square is the other side, 1 is the hypotenuse, then you can see that sin theta will be equal to square root 1 minus epsilon square. So instead of sin theta here we can substitute square root 1 minus epsilon square, so that will give you 1 minus epsilon square and 1 minus epsilon square will be cancelled. So we will get a value 1 plus e raised to minus epsilon into pi divided by square root 1 minus epsilon square. So this is the value of the percentage overshoot, maximum overshoot, peak overshoot, and to find the percentage overshoot we can multiply the value with 100, so that we will get e raised to minus epsilon pi divided by square root 1 minus epsilon square into 100. So this is the expression for peak overshoot. In order to find it, we have to find out C of t at t equal to Tp and also C of t at t equal to infinity, and we can substitute the values and find out this ratio, so that we will get the value of peak overshoot as e raised to minus epsilon pi divided by square root 1 minus epsilon square. Next is the settling time, that is the fifth time domain specification, settling time. And the response of the second order system has two components. They are decaying exponential component, that is e raised to minus epsilon into omega n into t divided by square root 1 minus delta square, and sinusoidal component, that is sin omega dt plus theta. And in this decaying exponential term dampens or reduces the oscillation produced by the sinusoidal component. Hence the settling time is decided by the exponential component, and the settling time can be found out by equating exponential component to percentage tolerance error. And therefore for 2% tolerance error, settling time at t equal to ts, settling time can be found out by substituting the value of ts in e raised to term, that is e raised to minus epsilon into omega n into ts divided by square root 1 minus epsilon square equal to 0.02. So for the least values of epsilon, e raised to minus delta omega n into ts will be equal to 0.02. You can see that when epsilon will be very small value, then the square root will be 1, so that we will get e raised to minus epsilon omega n into ts will be equal to 0.02. And in this case ts can be found out by taking the natural logarithm. So minus epsilon omega n into ts equal to ln natural logarithm of 0.02, that is equal to minus epsilon omega n into ts is equal to minus 4. So ts will be is equal to 4 by epsilon into omega n. In this case 1 by epsilon into omega n can be represented by the letter t, and ts will be equal to 4t, 4 into capital T, for 2% error. And see, when the error is 5%, error is 5%, you can see here, whenever the error is 5%, then we can get the settling time as e raised to minus epsilon into omega n into ts will be equal to 0.05. See here. And on taking the natural logarithm, minus epsilon into omega n into ts is equal to natural logarithm 0.05. So minus epsilon omega n into ts will be equal to minus 3, and the settling time is obtained by 3 by epsilon into omega n. 1 by epsilon omega n will be equal to t, therefore ts can be written as 3t. So settling time ts will be equal to 3 by epsilon into omega n, and that is equal to 3 into capital T for 5% error. And so in general we can write that settling time ts will be equal to ln percentage error divided by epsilon omega n, that is ln percentage error divided by t. Okay. So settling time for 2% error is 4 into t, that is equal to 1 by epsilon omega n. So actually the settling time എന്ന് പറയുമ്പോൾ ഇപ്പോൾ ഇത്ര നേരം പറഞ്ഞതിൽ നമ്മൾ ഓവർ ഡാംപ്ഡ് കേസാണ് ഡിസ്കസ് ചെയ്തത്. അണ്ടർ ഡാംപ്ഡ് കേസാണ് ഡിസ്കസ് ചെയ്തത്. അണ്ടർ ഡാംപ്ഡ് കേസിൻ്റെ റെസ്പോൺസ് നിങ്ങൾ അറിഞ്ഞിരിക്കണം, സി ഓഫ് ടി എന്താണെന്ന് അറിഞ്ഞിരിക്കണം. അപ്പോൾ അതിൽ 2 പാർട്ടുണ്ട്, ഒന്ന് എക്സ്പൊണൻഷ്യൽ ടേമും ഒന്ന് എന്ന് പറയുന്നത് സിനുസോയിഡൽ ടേമാണ്. അപ്പോൾ ഓസിലേറ്ററി നേച്ചർ ഉണ്ട് അതിൻ്റെ റെസ്പോൺസിന്. അപ്പോൾ ഓസിലേറ്ററി നേച്ചർ ഡീകേ ചെയ്യാൻ കാരണം ഈ എക്സ്പൊണൻഷ്യൽ ടേം ഉള്ളത് കൊണ്ടാണ് അത് ഡീകേ ചെയ്യുന്നത്. അപ്പോൾ സെറ്റിലിംഗ് ടൈം എന്ന് പറയുന്നത് നമ്മൾ ഒരു സ്റ്റെപ്പ് ഇൻപുട്ട് കൊടുത്തു കഴിഞ്ഞാൽ നമുക്ക് കറസ്പോണ്ടിങ് ആയിട്ട് ഔട്ട്പുട്ടായിട്ട് സ്റ്റെപ്പ് ഫോമിലുള്ള വേവ് ഫോം തന്നെയാണ് കിട്ടേണ്ടത്. പക്ഷേ അതിന് പകരം എന്താണ്, വേറെ വേവ് ഫോമാണ് കിട്ടുന്നത്. അപ്പോൾ അതിൽ തന്നെ ആ സ്റ്റെപ്പ് ഇൻപുട്ടിൻ്റെ ഫോമിലേക്ക് ആക്കാൻ വേണ്ടിയിട്ട് സഹായിക്കുന്ന കമ്പണൻ്റ് ഏതാണ്, എക്സ്പൊണൻഷ്യൽ കമ്പണൻ്റ് ആണ്. സിനുസോയിഡൽ കമ്പണൻ്റ് ഉണ്ടെങ്കിൽ കൂടിയും അതിനെ ഡീകേ ചെയ്യിച്ചിട്ട് കുറച്ച് ആ എറർ ഓസിലേറ്റിംഗ് നേച്ചർ കുറച്ച് കൊണ്ടുവരുന്ന ഈ എക്സ്പൊണൻഷ്യൽ ടേമാണ്. അപ്പോൾ നമുക്ക് ആ സെറ്റിൽ ചെയ്യാൻ, അതായത് അത് ഫൈനൽ വാല്യൂ ആയ 1ലേക്ക് യൂണിറ്റ് സ്റ്റെപ്പ് ആകുമ്പോൾ 1 എന്നുള്ള വാല്യൂയിലാണ് അത് എത്തുന്നത്. അപ്പോൾ അത് ആ സെറ്റിൽ ചെയ്യാൻ എടുക്കുന്ന ടൈം എന്ന് പറയുന്നത് നമുക്ക് എക്സ്പൊണൻഷ്യൽ ടേമിൻ്റെ ഹെൽപ്പോട് കൂടി കണ്ടുപിടിക്കാൻ പറ്റും. അതുകൊണ്ടാണ് നമ്മൾ എന്ത് ചെയ്യുന്നത്, ഇ റേസ്ഡ് മൈനസ് എപ്സിലോൺ ഒമേഗ എൻ ഇൻറ്റു ടി എസ് ഡിവൈഡ് ബൈ സ്ക്വയർ റൂട്ട് 1 മൈനസ് എപ്സിലോൺ സ്ക്വയർ ഈക്വൽ ടു 0.02, അതായത് 2% എററിന് കറസ്പോണ്ടിങ് ആണെന്ന് പറയുന്നത്. ഓക്കെ, അങ്ങനെയാണ് ആ ഇക്വേഷൻ വരുന്നത്. സോ എന്നിട്ടാണ് ബാക്കിയുള്ള കാൽക്കുലേഷൻ ചെയ്യുന്നത്. സോ വി ഗെറ്റ് settling time equation Ts for 2% error is equal to 4t, and for 5% error it is equal to 3t, and in general we can write it as settling time Ts is equal to ln percentage error divided by delta into omega n, that is equal to ln percentage error by capital T. See, this is all about time domain specifications. Most of the topics up to this class is a very lengthier topic, and you should by heart the equations, then only you can do the problems. Okay, that's all about this session.